Before the universe opened its eyes, before the first trembling shimmer of light carved itself into the dark, there existed a silence deeper than anything the human mind can hold. A silence without time, without space, without form. The camera drifts into this pre-cosmic void, a realm that is not a place, not an expanse, not a dimension. It is a stillness so complete that even the idea of nothingness becomes unstable, collapsing under the weight of its own paradox. Here, there are no directions to follow, no distances to cross, no future waiting to unfold. Only a frozen eternity that neither changes nor remains the same, because change itself has not yet been born. The darkness is unlit, but not empty. It feels suspended, as if holding a breath it does not yet know how to release. A vast, unseen canvas stretched across the brink of being, waiting for something, anything, to disturb its perfect quiet. Philosophers would later question whether this void ever truly existed. Whether nothing is an illusion shaped by limited imagination, a boundary drawn around ignorance, or a hidden ocean of unrealized potential where the laws of physics sleep in unawakened form. Perhaps this void was not absence, but the deepest kind of presence, a presence stripped of expression. And then, without warning, without cause, without a before to anchor the moment, something changed. A spark, a rupture, a first impossible flicker of becoming. Reality ignited, and the silence shattered. And in the wake of that primal awakening, a single haunting question lingers over everything that would ever come to be. What stirred the spark that created existence itself? Long before telescopes carved windows into the night, long before equations traced the skeleton of the cosmos, the question of origins drifted through human thought like an ancient tide. In the torchlit halls of early civilizations, philosophers contemplated a universe without precedent, wondering whether existence was sculpted from chaos, breathed from void, or eternally present with no beginning at all. Their ideas, wrapped in myth and metaphor, drifted across millennia, waiting for instruments and mathematics that did not yet exist. The camera drifts across the night sky, passing over constellations named by cultures who gazed upward and sensed a story unfolding above them. In Greece, Parmenides argued that creation from nothing was impossible. In India, hymns from the Rigveda questioned whether even the gods knew how the cosmos began. In China, cosmic eggs and silent voids shaped creation lore. These ancient reflections did not measure the universe, yet they sensed its weight, its mystery, its incomprehensible scale. Centuries later, the silence of the sky began to break. The invention of the telescope in the early 17th century changed everything. Through polished glass, the heavens revealed jagged details, moons orbiting Jupiter, shadows slicing across Saturn's rings, distant nebulae glowing like faint embers. But even then, the universe appeared static, a celestial sphere turning with eternal indifference. The cosmos, it seemed, had always been exactly as it was. The camera glides into the early 20th century, a world of chalk-dusted blackboards and quiet revolution. New mathematics had begun to unravel the invisible layers of reality. Building on the geometry of Riemann and the insights of Minkowski, Albert Einstein introduced general relativity in 1915, a theory of gravity not as a force, but as the curvature of space-time itself. Its equations, elegant and unsettling, held a secret that Einstein himself did not wish to confront. When applied to the universe as a whole, his field equations refused to remain static. They demanded motion, expansion or contraction, a cosmic choreography that contradicted centuries of philosophical comfort. Troubled by the result, Einstein introduced the cosmological constant, a delicate addition meant to stabilize the universe, freezing it in balance. He did not yet know that this act of resistance delayed, but could not halt, the revelation waiting just ahead. The camera now drifts through a quiet Belgian seminary, where a young priest-physicist named Georges Lemaitre pores over Einstein's equations. Unlike others, he embraces their implications. He sees a universe not anchored in eternal stillness but stretching outward, evolving like a living entity. In 1927, Lemaitre proposes a radical idea. The cosmos began from a single, hyperdense point, the primeval atom. A universe born from an initial moment, unfolding over time. It was a notion far ahead of its era, met with skepticism or gentle dismissal. The universe having a beginning felt unscientific, too reminiscent of creation myth. The scientific world was not yet ready. Yet far from Europe, atop a mountain overlooking Los Angeles, Mount Wilson, the quiet evidence was already gathering. The camera rises above the rugged ridges of the San Gabriel Mountains, settling before the dome of the 100-inch Hooker telescope. Inside, Edwin Hubble and his team work through the cold nights, measuring faint smears of light, nebulae once thought to lie within the Milky Way. But their motions, traced through spectral lines, tell a different story. Light from these distant systems stretches toward the red end of the spectrum. A subtle shift, a whisper from the cosmos suggesting motion. At first, the pattern seems coincidental. A few redshifts, then more, then dozens. Hubble plots them against distance, measured by painstaking observations of Cepheid variables, standard candles flickering across the abyss. The result is unmistakable. The farther a galaxy lies, the faster it moves away. The camera sweeps outward, showing galaxies like drifting lanterns in an ever-expanding ocean of dark. Hubble's discovery is not noisy, not theatrical. It happens in silence, a quiet set of points on a graph that overturns the world. Einstein visits Mount Wilson soon after, peering through the same telescope whose observations contradict his belief in cosmic stasis. According to later accounts, he confesses the cosmological constant to be his greatest blunder, though modern interpretations are more nuanced. Regardless, the moment marks a shift. The universe is not eternal and unchanging. It is dynamic. It is expanding. The implications are profound. If everything is moving apart now, then at some point in the past it must have been closer, unimaginably closer, compressed into a state that defies classical physics. The idea of a cosmic beginning, once philosophical speculation, becomes a scientific necessity. Yet the early cosmologists do not grasp its full weight at first. They debate whether redshifts truly represent expansion or are caused by some unknown process, tired light, gravitational effects, or atmospheric distortions. But the data grows too precise, too consistent. Instruments sharpen. Spectrographs improve. Observations expand beyond Mount Wilson, revealing more galaxies, more redshifts, a deeper and broader cosmic pattern. The camera moves through observatories across the world. Palomar, Yerkes, Lowell, each refining the view. Astronomers begin to construct the first evolutionary models of the universe. The notion of a beginning shifts from speculation to central hypothesis. Lemaitre's primeval atom re-emerges, now supported by expanding evidence. A quiet scientific revolution unfolds. The universe is not a static cathedral but an unfolding story, with a starting point buried beyond the reach of ordinary time. Yet something is missing, a cosmic echo, a remnant, a signature from the earliest moment itself. Without it, expansion remains a clue, not a confirmation. For decades, cosmologists search for evidence of the universe's birth, a relic of extremely high temperature and density predicted by theorists like George Gamow and Ralph Alpher. And then, quietly and unexpectedly, the universe delivers. The camera drifts to the rooftop of Bell Laboratories in New Jersey, where two radio engineers, Arno Penzias and Robert Wilson, attempt to eliminate a persistent background noise in their antenna. The signal is faint, uniform, omnipresent. They clean the instrument. They adjust the electronics. They remove nesting pigeons. Nothing changes. This hiss, this thin radiation bathing the entire sky, is not noise. It is the afterglow of creation itself. Though this crucial discovery belongs to the next chapter's deeper investigations, its shadow belongs here, in the discovery phase. It becomes the final quiet confirmation that the cosmos had a beginning, a moment of incandescent birth whose fading glow still washes across Earth. The camera pulls back into the blackness between galaxies. What emerges from this chapter is not yet explanation, not yet theory, but awareness, the dawning realization that the universe is neither eternal nor unchanging. It had a beginning, and that beginning, fragile, violent, and almost incomprehensible, is the mystery that will haunt every generation of scientists who follow. The first hints of a cosmic beginning spread through the scientific world like a tremor moving beneath ancient stone, subtle, almost inaudible, yet carrying the power to topple everything built upon it. The idea that the universe had emerged from a moment of absolute density did not begin as revelation. It began as discomfort, a quiet disturbance, a violation of intuition so profound that even those who witnessed the evidence hesitated to believe it. The camera opens on the intergalactic void, an immense, oceanic darkness stretching in all directions. Galaxy clusters float like drifting archipelagos, their light trembling across the abyss. In this silence, the immensity of what scientists were being asked to accept becomes palpable. All of this grandeur, all structure and starlight, once compressed into a point smaller than an atom. A universe crushed into a seed of impossible density, where space-time itself folded into near-nothingness. Classical physics could not tolerate such a state. It had been built on continuity, determinism, and infinite time, a cosmos without abrupt beginnings or ends. From Newton through the 19th century, the universe was assumed eternal, a vast celestial clock ticking without origin. Its laws were stable, its existence unbounded. No physicist trained in the traditions of classical mechanics could imagine the cosmos erupting from a singular event. The camera glides through a 19th century observatory, dust floating like motes of time in warm lamplight. Astronomers chart orbits and calculate celestial motions with exquisite precision, all under the assumption that the heavens follow a timeless rhythm. The universe they envision is infinite and unchanging, its expansion or contraction unthinkable. Even thermodynamics, emerging in that era, implies an eternal past. If the universe had a beginning, why had it not already reached thermal equilibrium? The idea of a beginning was not merely scientifically strange, it was philosophically destabilizing. The camera shifts to a quiet study, books stacked in towering columns. Here, the age-old discomfort resides, creation ex nihilo, the emergence of something from nothing. Philosophers across cultures had recoiled from this paradox. Nature abhors discontinuity. Existence, they argued, must arise from prior existence. To imagine otherwise was to imagine a miracle, not a mechanism. Then came Einstein. His field equations, introduced in 1915, offered a revolutionary interpretation of gravity and spacetime. But when applied to the cosmos as a whole, they refused the comfort of eternity. They insisted on dynamism, a universe in motion. Einstein's reaction revealed just how deeply the scientific world feared a beginning. Unable to accept the implication, he added the cosmological constant, a deliberate constraint, to force the universe into stasis. This was not error, it was refusal. The camera pivots toward Einstein's chalkboard, filled with curves of spacetime, symbols bending under mathematical tension. In these lines lies the battle between expectation and truth. Even Einstein, whose insights shaped modern cosmology, resisted the idea of a universe that once did not exist. But the data was patient. When Hubble's redshifts emerged, when galaxies retreated like fading embers in an ever-widening night, the first shock wave rippled through theoretical physics. Expansion implied compression, and compression implied a beginning, one so violent and fundamental that language strains to describe it. The camera plunges toward a conceptual singularity, a point of blinding density where space-time collapses into an undefined state. No distance, no dimension, no before. This is the birthplace classical physics could not enter. Equations diverge. Densities reach infinity. Curvature becomes undefined. Mathematics, normally a steady companion, breaks apart under the weight of such extremity. The existential severity of the singularity becomes clear. It is not a physical object but a place where the known laws of nature fail. For early scientists, this failure was too immense to accept. Many chose skepticism over submission. The camera drifts into the conference halls of the early 20th century. Physicists gather around blackboards, their discussions hushed, uneasy. Some suspect observational error. Others propose alternative mechanisms, exotic forces stretching light, unknown properties distorting spectra. To believe the universe had a beginning required abandoning the framework that had guided physics for centuries. And beneath this intellectual resistance lay a quieter emotional truth. The birth of the universe felt too large, too final. It suggested boundaries, not spatial boundaries, but conceptual edges. A moment beyond which physics could not exist. A veil scientists were forced to acknowledge but forbidden to cross. Even those who embraced the implications felt the tremor. When Lemaitre presented his primeval atom model, the scientific establishment pushed back, insisting it sounded too theological. The discomfort revealed something unspoken. A universe with a beginning seemed to demand deeper answers. Answers no telescope or equation had yet provided. The camera descends into the subatomic realm, showing a landscape of quantum fields shimmering with uncertainty. Here, the idea of extreme density grows even more troubling. As densities approach the Planck scale, quantum mechanics and general relativity collide violently. Their incompatibility becomes the heart of the crisis. The two pillars of modern physics refuse to coexist in the environment of a singular beginning. This is the true scientific shock. The origin of the universe exposes a fracture in the foundation of physical law. The equations of general relativity predict singularity. Quantum mechanics denies it. Reality lies in between, someplace neither theory can describe. The camera returns to the cosmic scale, showing the early universe as a blinding, turbulent plasma. This is the closest science can come to the beginning, a fraction of a second after the supposed singularity. Anything earlier dissolves into speculation. Every measurement that followed, redshift surveys, cosmic expansion rates, temperature uniformity across the sky, only deepened the shock. As data grew more precise, the mystery sharpened. Not only did the universe have a beginning, but that beginning was stranger than anyone expected. Too smooth, too hot, too uniform, too fine-tuned. The early universe was not chaotic. It was exquisitely arranged. The camera glides over the cosmic microwave background, ripples of ancient heat faintly etched across the sky like fingerprints of creation. These patterns contain no hint of disorder. Instead, they reveal a universe that emerged already predisposed toward structure, gravity, and form. This was not merely a beginning. It was a beginning with intent, not metaphysical intent, but mathematical precision. For scientists of the time, the shock was not philosophical alone. It was empirical. The evidence pointed to a singular, sharply defined origin, one that did not fit within the boundaries of known physics. The final image of the chapter shows the universe expanding outward, galaxies drifting apart in silent acceleration, as though pushed by an unseen force. The singularity sits behind them like an unreachable horizon, the point where everything began and where understanding collapses. The shock remains, a universe with a beginning, the point where physics fails. A mystery so vast that it reshaped the trajectory of science itself. And from this fracture in understanding, a deeper descent begins, into theories, observations, and questions that will attempt, but never fully succeed, to reconcile the impossible. The chapter opens in a vast, frozen silence. The intergalactic void stretched across billions of light years, its darkness threaded with the faintest glow of ancient radiation. The camera glides slowly toward this invisible ocean, revealing not stars, not galaxies, but a subtle tremor embedded within space-time itself, the fading echo of the universe's first light. It is here, in this near-perfect uniform glow, that the search for cosmic beginnings deepens beyond speculation and into evidence. Evidence carried across the cosmos since the universe was only 380,000 years old. The discovery is almost accidental. The camera descends toward a quiet hilltop in New Jersey, to the enormous white horn antenna of Bell Laboratories. It is 1964. Arno Penzias and Robert Wilson, two radio engineers, aim to calibrate their microwave receiver. A faint hiss contaminates every measurement, a soft, unyielding static. They clean the system, scrub the metal, remove nesting pigeons and their debris. Yet the hiss remains, uniform, ever-present, coming from every direction in the sky. Unbeknownst to them, a team of physicists at Princeton, Robert Dick, Jim Peebles, David Wilkinson, is already searching for the relic radiation predicted by Big Bang models. When word reaches Dick's group about the strange signal from Bell Labs, his quiet response becomes a historic understatement. "Well, boys, we've been scooped." The camera lifts into the sky, passing through atmospheric haze into the raw emptiness beyond. The faint microwave hum discovered by Penzias and Wilson blankets the universe. This is the cosmic microwave background, the CMB, the afterglow of a universe once so hot and dense that matter and light were fused into an inseparable plasma. When the cosmos cooled enough for atoms to form, light finally broke free, traveling outward for nearly 14 billion years to reach Earth as a cold, ancient whisper. Its existence answers one question, but opens 1,000 more. The camera now moves through a glowing sphere of early universe plasma, turbulent and shimmering. Quantum fluctuations ripple across its surface, microscopic variations in density shaped by uncertainty itself. Inflation, a hypothesized burst of exponential expansion, stretched these quantum ripples across cosmic scales, seeding the structures that later became galaxies and clusters of galaxies. A mechanism so precise that its fingerprints appear in temperature differences no larger than 1 part in 100,000. To find these fingerprints, humanity needed new tools. The scene transitions to 1989. The COBE satellite lifts into orbit, a fragile emissary sent into the cold darkness to measure the CMB with unprecedented accuracy. COBE returns with 2 profound results: a perfect blackbody curve, proof that the universe began in a hot, dense state, and a faint mottled pattern across the sky. The anisotropies, the tiny fluctuations that would grow into everything we see. These patterns are delicate, almost ghost-like. Yet in their subtle variations lies the universe's blueprint. Temperature differences measured in microkelvins reveal regions where matter gathered or dispersed. In these faint ripples, the cosmos wrote its first structures. But as the resolution increases, so does the mystery. The fluctuations are not entirely random. The camera drifts across the CMB as if skimming across the surface of an ancient cosmic ocean. Certain regions appear strangely aligned, the so-called axis of evil. Others possess anomalous cold spots, vast regions with temperatures lower than models predict. These gaps and peculiarities whisper of hidden physics, or unexplained cosmic features, or perhaps an early universe event not yet understood. The descent deepens. The camera leaves the microwave glow behind and plunges into the subatomic realm, a space where classical geometry dissolves. Here, in the quantum vacuum, fields fluctuate restlessly even at absolute zero. Energy is never still. Particles flicker into existence and vanish. This sea of zero-point energy is believed to have shaped the earliest moments of the universe, an unstable expanse where virtual particles and quantum fields ignited the inflationary burst. Yet this explanation does not quiet the confusion. It sharpens it. Vacuum energy is real, measured in the Casimir effect, observed in quantum field theory, but its predicted value is catastrophically too large. Quantum calculations suggest a vacuum energy density 10 superscript 1 superscript 2 times greater than what cosmology observes. The most extreme mismatch in all of physics. A rift between 2 great theories, quantum mechanics and general relativity, becomes impossible to ignore. The camera now enters a conceptual landscape, a space-time diagram showing the earliest fractions of a second after the Big Bang. Inflation flattens space, stretches quantum ripples, and wipes the cosmos clean of irregularities. But the cause of inflation, the field that drove it, the conditions that ended it, remains unseen. Cosmologists name it the inflaton, but they know only what it must accomplish, not what it truly is. WMAP arrives in 2001, sharpening the CMB map with unprecedented clarity. The universe's age is pinned down with extraordinary precision. The distribution of matter is measured. The geometry of the cosmos is revealed, flat to within a hair's breadth. Inflation's fingerprints grow clearer. Then comes Planck in 2009, offering the most detailed portrait of the CMB ever captured. The camera rests gently over its full-sky image, a swirling mosaic of ancient radiation, intricate and delicate as frost patterns on cosmic glass. Planck exposes the CMB's multipole moments, polarization patterns, and acoustic peaks, each one a coded message from the first moments of cosmic evolution. Yet the closer scientists look, the stranger the universe becomes. The large-scale anomalies persist. The cold spot remains. The alignment across hemispheres challenges assumptions of isotropy. The early universe expansion rate clashes with measurements from modern galaxies, the now famous Hubble tension. A disagreement so sharp that some physicists suspect a break in lambda CDM, the standard model of cosmology. The investigation plunges deeper still. The camera moves into darkened laboratories, where liquid helium cools superconducting detectors to temperatures near absolute zero. Here, experiments probe quantum fields searching for hidden symmetries, inflationary relics, and hints of primordial gravitational waves, tremors from the earliest instant of spacetime itself. The BICEP arrays stare toward the South Pole sky, hunting for the subtle polarization patterns that inflation should have left behind. The search continues through dust, noise, and uncertainty. Meanwhile, theorists descend into the mathematics of quantum origins. They explore the Wheeler-DeWitt equation, which removes time entirely, proposing a universe emerging from a timeless quantum wave function. Some investigate loop quantum cosmology, where the singularity is replaced by a bounce, and the universe cycles through contraction and expansion. Others examine vacuum decay, the idea that our universe sits in a metastable state that once tunneled into existence through quantum fluctuation. All of these theories attempt to peel back one more layer, but each reveals new contradictions. The camera moves into the interstellar void, a sea of darkness pierced by starlight. It lingers on a single photon traveling since the dawn of the universe, carrying information across epochs. Its journey symbolizes the greatest challenge of all. No matter how precise our instruments become, they cannot observe the moment before the CMB was released. The earliest 10 superscript 3 seconds remain hidden behind a cosmic horizon, where quantum gravity dominates and classical spacetime fails. Every tool, from COBE to WMAP to Planck, has revealed exquisite detail. Every layer peeled back has exposed a deeper riddle. A universe that begins in perfect smoothness despite quantum chaos. Temperature uniformity across regions that never had time to communicate. An expansion too precisely calibrated to be random. An origin that defies the merger of quantum field theory and general relativity. The camera pulls back. Galaxies swirl in slow spirals. Nebulae bloom like cosmic flowers. Dark voids yawn with ancient depth. And beneath all of it, the faint microwave whisper continues. The last surviving memory of a universe struggling to be understood. The deeper the investigation goes, the clearer one truth becomes. The universe is not merely expanding. It is guarding a secret hidden in the earliest light, the faintest temperature ripples, and the impossible calm of the moment where physics breaks. That a quiet tremor ripples through the foundations of modern cosmology, so soft at first that it feels like an illusion, a whisper in the equations. Yet with every attempt to illuminate the universe's first second, the tremor grows. It becomes a vibration in the deepest theories, then a fracture in the laws that once felt unbreakable. The camera drifts through an ocean of ancient photons, the dim afterglow of creation shimmering like dust suspended in eternal twilight. But beneath this serenity lies a tension scientists cannot smooth away. Every map of the cosmic background radiation, every model of the universe's infancy, every calculation pressed to the edge of time itself carries the same unsettling message. The origin of everything does not behave. Inflation expands the early universe at speeds beyond imagination, faster than the limits relativity was built to define. Quantum mechanics seeds spacetime with fluctuations so violent they should have torn existence apart before it ever began. And relativity, beautiful, precise, unyielding, refuses to describe anything before the cosmic clock reads zero. Then come the anomalies. A mysterious alignment across billions of light years. Cosmologists call it the axis of evil. A cold scar in the cosmic microwave background, too massive, too empty, too improbable. And the impossible uniformity of the universe itself, as if distant regions were once connected, though relativity insists they never could have been. In this silence, the mystery deepens. The universe feels less like a solved equation and more like a riddle older than time, pressing outward from the darkness, demanding to be understood. The universe, on its largest scales, appears calm, a nearly flawless expanse of ancient light frozen in a temperature only fractions of a degree above absolute zero. Yet beneath that stillness lies an unfolding crisis, one invisible to the cosmos itself but deeply felt by the minds studying it. Every attempt to reconstruct the first second of existence, every model of inflation, every quantum gravitational speculation, presses modern science toward a cliff where known physics simply dissolves. The journey begins with inflation, the briefest and most violent transformation the universe has ever undergone. For a sliver of a moment, far shorter than the blink of a subatomic particle, space erupted outward with exponential speed. Galaxies, clusters, cosmic filaments, all still unborn, were carried within a storm of expansion so ferocious that even light lagged behind. Inflation did not merely stretch the universe, it flung it open with a force that defied comprehension. The camera glides through a simulation of this early fury, a foaming quantum sea, expanding faster than the mind can follow, each wave crest seeding the structures that would one day become galaxies. Yet no matter how elegantly inflation explains the universe's smoothness and scale, it breaks something essential. For according to relativity, nothing, not matter, not energy, not information, may outpace the speed of light. But inflation did. Not once. Not momentarily. Continuously. Cosmologists reconciled this contradiction by noting that it was not objects moving faster than light, but space itself swelling beneath them. Still, the unease lingered. The theory solved problems while simultaneously birthing new paradoxes, a reminder that the universe behaves more like a poem than an equation. As the camera drifts deeper, moving across the faint wrinkles of the microwave sky, another fault emerges: quantum mechanics. In the earliest instance, quantum fluctuations were magnified to cosmic scales. These minute ripples, absurdly small, smaller than particles themselves, were blown large enough to pattern the universe, determining where galaxies would form and where voids would remain eternally empty. But quantum theory also predicts something else. Something darker. If the early universe hosted fluctuations of maximum possible violence, their intensity should have shredded spacetime, turning existence into a quantum froth too unstable to persist. Yet the universe survived. It expanded, cooled, structured itself, and eventually gave rise to worlds, oceans, and observers capable of asking impossible questions. The contradiction remains unresolved. The universe should not be here in its present form, yet it is. And the laws designed to describe it do not agree on how. Relativity paints a universe of smooth, continuous spacetime, a fabric that curves under the weight of matter. Quantum mechanics describes reality as granular, jittering, ambiguous. When cosmologists drag both theories toward the beginning of time, toward densities so extreme that the very concept of space begins to break apart, they find not harmony, but collision. The equations explode into infinities. Curvature climbs without limit. Temperature spikes beyond meaning. There is no stable solution, only a wall of mathematical fire. The camera slows as it approaches that wall, a luminous horizon, trembling with energy and uncertainty. Beyond it lies the forbidden territory before the Big Bang, a region relativity refuses to describe. In this silence, cosmology loses its footing. Then, just as physicists grapple with these fractures, new anomalies emerge, artifacts imprinted in the sky itself. They come not from theory, but from observation, and their message is equally troubling. The cosmic microwave background, when mapped with exquisite precision by satellites like WMAP and Planck, reveals an eerie alignment, a vast cosmic structure stretching across the observable universe. A subtle pattern in the temperature variations appears to point in a single direction, as if an axis threads through the entire sky. Cosmologists, half jokingly and half unsettled, name it the axis of evil. Its existence defies a core expectation that on the largest scales, the universe should have no preferred direction. Yet the alignment persists, whispering of symmetry broken for reasons unknown. Another anomaly sits deeper in the map, a massive cold region spanning hundreds of millions of light years. It is emptier than theory predicts, colder than the surrounding cosmos, and too improbable to dismiss. Some argue it may be a supervoid, others suggest it could be an imprint from before the Big Bang itself, a hint of collisions between universes, or scars etched into space-time by events predating creation. The camera drifts over this cold expanse, a dark bruise in the fabric of ancient light. It feels like a message, though its meaning lies beyond reach. But perhaps the most unsettling mystery is the universe's long-distance uniformity. Regions of space separated by tens of billions of light years, too far apart to have ever exchanged light or information, nonetheless share the same temperature to 1 part in 100,000. Relativity insists those regions were never in causal contact. Yet the data says otherwise. They behave as though they were once intimately connected. Inflation attempts to explain this by rewinding the cosmic film, pulling everything back to a time when all of space was compressed into a tiny, uniform state. But even inflation requires initial conditions so fine-tuned that they hint at a deeper layer of physics, one hidden behind the veil of the earliest moments. The mystery deepens. Why did inflation start? Why did it stop? Why did it behave with such perfect mathematical precision? No law demands this. No equation predicts it. Inflation is less a solution than a placeholder for an unknown engine driving the birth of spacetime. As the chapter unfolds, the camera drifts outward, from the CMB maps glowing like ancient parchment to the vast cosmic web stretching across the universe. Galaxies trace filaments shaped by quantum ripples in the first instant, yet the patterns scale borders on the miraculous. It is as though the universe remembers something, an echo, a symmetry, a boundary condition impressed upon it long before classical physics began to operate. Cosmologists attempt to peer further, probing depths where neither quantum theory nor relativity can be trusted. They explore models where spacetime emerges from entanglement, where universes bud from quantum fluctuations, where inflation never ends but spawns infinite cosmic domains. Each attempt reveals contradictions, paradoxes, or new mysteries, as if the universe is guarding its origin with layers of complexity. The emotional undercurrent builds, a quiet awe mixed with an existential tremor. The origin of everything does not merely break rules. It behaves as though no rules existed. It is a frontier where logic falters, where time loses meaning, where the universe appears less like a physical system and more like a horizon of unknowability. In the end, cosmology stands in a place that feels both dizzying and sacred. The first second of the universe is no longer a solved moment, but a labyrinth. A region where every answer reveals another hidden chamber of mystery, where the deepest understanding dissolves into deeper questions. The chapter closes as the camera pulls back from the cosmic microwave background, the mottled glow fading into the darkness of intergalactic space. In that silence, the truth becomes clear. The origin of the universe is not simply unknown. It is unknowable by the very rules that govern reality today. To understand the beginning, physics must become something new. And the search continues. The universe has never surrendered its beginning easily. Every law that governs the stars, every equation etched into the foundations of physics, seems to unravel when pushed to the edge of creation. And so, across the last century, cosmology has become a lantern held against a horizon where mathematics trembles and the familiar dissolves. The camera glides through a quiet sea of nebulae, vast clouds glowing in crimson, sapphire, and gold, cradles of new worlds suspended in the dark. Their slow, luminous forms echo a deeper truth. Creation is rarely gentle and never simple. Behind their beauty lies violence, pressure, collapse, ignition. And behind the universe's birth lies something stranger still. To understand that moment, scientists turned not to one idea but to many, each bold, each elegant, each incomplete. Hawking envisioned a cosmos with no boundary, where time curves like the surface of a sphere, erasing any notion of before. Loop quantum cosmology imagined a previous universe collapsing into a quantum heartbeat, rebounding into ours. String theory pictured entire cosmic membranes drifting through a higher dimensional ocean, colliding to spark existence itself. Eternal inflation painted a landscape of infinite universes blossoming in a fractal storm of creation. And the quantum vacuum, restless, seething, alive, suggested that perhaps reality emerged from fluctuations in a field that never truly rests. Each theory stretches the mind. Each explains something the others cannot. Each collapses under its own questions. In the silent gulf between them lies the growing realization that the universe is not simply older than thought. It may be deeper, layered, cyclic, or boundaryless. A cosmos whose origin hides behind the limits of imagination itself. The search for the universe's beginning has always carried the weight of philosophy, the precision of mathematics, and the courage to imagine realities far beyond instinct. As cosmologists traced the universe backward, from galaxies to hydrogen, from plasma to quantum foam, they encountered a barrier, a moment where the known laws of physics shattered. And so began a deeper journey, one not confined by the familiar architecture of space and time. The first great vision belongs to Stephen Hawking, whose no-boundary proposal emerged from a fusion of quantum theory and general relativity. In this model, the universe has no sharp beginning, no singular edge where time erupts from nothing. Instead, the camera drifts toward a curved, four-dimensional surface, a cosmic sphere where before loses meaning. Time, in Hawking's picture, behaves like a spatial dimension at the earliest moment. There is no point where the cosmos begins. There is only smoothness, like the rounded tip of an egg. The universe does not burst from a void. It unfolds. This idea carries a profound serenity. A universe without boundaries cannot be cut open or isolated. It simply exists, expanding not out of nothing but out of a geometry that needed no cause. Yet the theory wavers under scrutiny. The mathematical conditions required are delicate, heavily dependent on assumptions about quantum gravity that remain untested. Still, its poetry persists, a cosmos with no origin because origins are illusions. The camera glides from this abstract sphere into a denser, vibrating landscape, the domain of loop quantum cosmology. Here, space-time is not smooth but granular, woven from discrete loops of geometry that shrink only to a finite size. In this framework, the Big Bang is not a beginning at all, but a bounce, the echo of a previous universe collapsing inward. As densities rise, a repulsive quantum force emerges, preventing total collapse. Instead, the cosmic fabric rebounds, hurling itself outward into a new expansion. This theory offers a striking reversal. Instead of a singularity, there is continuity, a rhythmic pulse of cycles, contraction leading to expansion in an eternal cosmic breath. But mysteries remain. What determined the conditions of the previous universe? Why does the bounce produce a universe so remarkably smooth, so exquisitely tuned for structure? The equations hint at answers but not conclusions. The camera lingers on a glowing loop of geometry, shimmering with untested promise. From here, the scene shifts to a realm shaped not by loops but by strings, vibrating filaments so small they transcend detection. In the vast mathematical architecture of string theory, the universe is not limited to the familiar three dimensions of space. A higher dimensional expanse unfolds, one where entire universes can exist as membranes, floating like luminous sheets in a hidden ocean. These branes drift, ripple, and occasionally collide. And in one such collision, a shockwave of unimaginable scale could ignite a Big Bang. This idea, called the ekpyrotic model, replaces a singular beginning with an event, a cosmic impact between higher dimensional worlds. The camera shows two immense membranes drifting toward one another, their surfaces quivering with quantum vibrations. When they meet, an explosion of heat and light bursts forth, our universe expanding into being. It is a vision at once majestic and unsettling. It explains the universe's uniformity, its large-scale smoothness, its early conditions. Yet it also raises questions. What lies beyond the branes? What set them into motion? Are collisions rare or endless? String theory offers landscapes of possibilities, yet little experimental guidance. Still, the concept of creation as collision remains one of the most cinematic visions ever proposed. The chapter deepens as the camera rises into the cold immensity of eternal inflation, a realm where inflation did not end everywhere at once. Instead, it stabilized only in isolated regions, allowing pockets of space to cool and form universes, while elsewhere the expansion continued unchecked. This eternal inflation stretches onward without end, spawning universes the way a storm breeds waves, each bubble disconnected, each with its own physical laws, each floating in a vast, inflating sea. Our universe becomes one bubble among countless others, an island of stability in an infinite archipelago of cosmic domains. The camera drifts among these bubbles, glowing like fire-lit lanterns on a dark, interdimensional ocean. The philosophical weight deepens. If this model is true, our universe is simply one story, not the story. Physics becomes a chapter in a book without final pages. Yet eternal inflation carries its own contradictions. The mathematical structure may produce infinities that defy probability. Predictions become almost impossible. And the theory risks explaining everything, and therefore nothing. The camera dives now into the deepest realm, the quantum vacuum. This is not emptiness but a roiling sea of energy, where virtual particles flicker in and out of existence and fields swirl with restless motion. Some cosmologists propose that the universe may have emerged from a fluctuation within this quantum field, an instability that caused space-time itself to blossom from the vacuum. In this vision, creation is not the product of a cause but of inevitability. The vacuum cannot remain perfectly still, its fluctuations demand expression. A universe becomes not an exception, but a natural event, one among many potential realizations of quantum possibility. The idea is breathtaking, existence as a ripple in a field that never sleeps. Yet it invites an even deeper question: why does the quantum vacuum exist at all? What is the origin of the fields that give rise to space, time, and energy? These questions loom uncomfortably beyond the reach of current theory. As the camera retreats from these speculative landscapes, from brains to bubbles, from bounces to boundless geometries, a single theme emerges. Each theory illuminates a corner of the mystery. Each answers one riddle while spawning others more profound. The origin of the universe becomes a hall of mirrors. Every reflection reveals depth, yet no reflection reveals truth. The emotional undercurrent grows as the narration reflects on the limitations of knowledge. The universe's beginning may lie beyond the conceptual vocabulary of modern physics. Perhaps time itself dissolves before reaching the origin. Perhaps causality fails. Perhaps the universe is older, stranger, layered in ways the human mind cannot easily grasp. The camera drifts into a supermassive black hole's accretion disk, matter swirling like a luminous whirlpool around the dark heart of gravity. In this extreme environment, space-time bends toward the edge of comprehension. Scientists suspect that understanding such singular regions may one day illuminate the birth of the cosmos. But even here, quantum gravity remains elusive, a missing key that could unify every theory explored within this chapter. The chapter closes with the camera rising above the cosmic web, galaxies glowing like embers in an infinite night. The universe stretches outward, majestic and indifferent, carrying its secrets behind curtains woven from uncertainty. And the narration settles on the central realization. The beginning of the universe is not a single answer waiting to be found. It is a frontier where every explanation expands the mystery, and every theory points beyond itself, toward a truth the cosmos has not yet allowed us to see. In the silence between galaxies, where light thins into a pale whisper and gravity grows faint, the universe hides the faintest traces of its beginning. Not in stars, nor in nebulae, nor in the coiling arms of galaxies, but in relics older than structure itself. The first flashes, the first vibrations, the first breath of spacetime. Yet these clues are so distant, so faint, so deeply entombed in the fabric of reality that only the most delicate instruments ever constructed can reach them. The camera drifts across Earth's night side, cities glowing like soft constellations, before rising toward a golden mirror suspended in the void. The James Webb Space Telescope, petals open, listening to the ancient light. Its sensors stretch across wavelengths long extinguished in the visible universe, reaching back toward cosmic dawn. Far below, lasers in vacuum tunnels pierce the ground, arms of LIGO trembling with quantum precision, waiting for ripples from the universe's first instant. In the cold of Antarctica, detectors stare into the sky, catching whisper-thin neutrinos. On orbiting platforms, microwave instruments search for patterns older than atoms. And in vast underground caverns, particle accelerators simulate energies where the universe first learned to exist. Humanity has built these machines not to conquer the cosmos, but to approach its origin with humility, fragile tools dwarfed by forces they seek to understand. Each device asks the same impossible question: what happened at the beginning? And in their signals, their noise, their faint, mysterious patterns, lies the haunting possibility that the universe left a message, etched not in language, but in radiation, curvature, and vibration. A message that may yet reveal how time itself opened its first eye. The pursuit of the universe's beginning has become the greatest experiment ever attempted by a species made of dust. To reach back through 13.8 billion years, humanity cannot rely on memory or myth. Instead, it must construct instruments capable of touching the earliest light, the earliest waves, the earliest changes in the cosmic fabric. Machines must become the fingers that reach where history dissolves into physics. The first machine stands far from Earth, basking in the sun's distant glow, the James Webb Space Telescope. Its gold-plated mirrors glimmer like a cosmic petal, unfolding in the darkness beyond the moon. Webb does not merely look at stars. It listens to wavelengths stretched by time itself, infrared signals from galaxies so ancient they formed when the universe was scarcely a few 100 million years old. The camera glides toward a young galaxy Webb once captured, a faint ember draped in hydrogen fog. Its light began its journey before the Milky Way was born. Webb's data reveals that even in the universe's early youth, structures emerged with startling speed, an unanticipated efficiency that hints at processes not yet fully understood. Some galaxies appear too massive, too luminous, too mature for their cosmic age, unsettling long-held assumptions about the early timeline. Yet Webb was built not only for galaxies. Its most profound quest is to detect the faint glow of the first stars, population 3 giants forged from pristine hydrogen and helium, their cores igniting before metals existed. These stars remain elusive, hidden in the distant haze. If Webb ever detects their spectral fingerprints, cosmology will step closer to understanding the universe's first attempt at light. As the camera drifts away from Webb, the scene dissolves into a quiet Earth valley beneath a sky stitched with stars. Here, enormous concrete tunnels stretch like arms of a sleeping titan. LIGO, the Laser Interferometer Gravitational Wave Observatory. Inside, lasers bounce across vacuum chambers with precision so fine they can sense a change smaller than a proton's width. When two black holes collide, they send ripples through space-time, waves that LIGO can hear as faint tremors in the silence. These detections have opened a new window on the universe, revealing mergers billions of light-years away. But LIGO's most ambitious goal lies far beyond black hole collisions: primordial gravitational waves. Ripples from the universe's first moments. Waves generated when inflation stretched space-time faster than light could traverse it. These waves would be the oldest signal in existence, older even than the cosmic microwave background, older than atoms, older than matter itself. If detected, they would provide direct evidence of inflation's violent expansion. But their signal is unimaginably faint. LIGO is not yet sensitive enough. And so, humanity builds more tools. High in the Andes, on Antarctica's plateau, and aboard balloons drifting above the atmosphere, telescopes point toward the cosmic microwave background, searching for subtle swirling patterns, B-modes, caused by those primordial waves. So far, nature has remained silent. The patterns remain hidden, buried beneath dust, noise, and cosmic confusion. And yet the pursuit continues. The narration sinks deeper as the camera moves underground into the whispering tunnels of a particle accelerator. Here lies another frontier, recreating the forces that shaped the universe's earliest moments. In the Large Hadron Collider, protons collide with energies approaching those of the infant cosmos. These collisions do not recreate the Big Bang, but they probe the same temperatures and symmetries. From them, physicists hope to find clues about the unification of forces, moments when gravity, electromagnetism, and the nuclear interactions may have behaved as one. If those symmetries can be understood, the universe's earliest conditions will come into sharper focus. Questions ripple through theoretical frameworks. Did hidden dimensions influence the Big Bang? Did exotic fields seed inflation? Did unknown particles dominate the first microsecond? Each collision in the accelerator is a question hurled at the boundary of knowledge. Each shower of particles is the universe's partial reply. The chapter deepens as the camera enters a region filled with pulsars, dense, rapidly spinning neutron stars emitting beams of radio light. Their pulses beat like cosmic metronomes. By measuring their timing with exquisite accuracy, astronomers create a galactic-scale detector. When gravitational waves ripple through the Milky Way, they stretch and compress the distances between Earth and these pulsars, subtly altering the rhythm of the pulses. This technique, pulsar timing arrays, is now sensitive enough to detect low-frequency waves caused by the slow dance of supermassive black holes. But beyond them lies a deeper hope, the signature of gravitational waves from the universe's earliest instance. If these tools succeed, they will reveal the first trillionth of a second, an epoch when the universe's energy density surpassed all known limits, when quantum fluctuations sculpted the blueprint of cosmic structure. The narration shifts now to the realm of satellite missions. The Planck satellite once mapped the cosmic microwave background with unprecedented precision, revealing temperature variations only millionths of a degree apart. These variations, tiny ripples stretched from quantum origins, serve as the universe's oldest map. Yet even Planck found anomalies. A cold spot without explanation, an apparent axis of alignment stretching across the sky, patterns that whisper of unknown processes. Future missions hope to clarify these mysteries. Concepts like Lightbird, PICO, and CMB-S4 aim to measure the microwave background with sensitivity approaching the theoretical limit. They seek inflation's fingerprints, minute distortions in polarization patterns that would confirm or challenge the story of cosmic expansion. But even these are not enough. To reach deeper still, humanity must go beyond Earth, beyond the solar system, into the deep space between planets. Proposals for next-generation detectors imagine spacecraft separated by millions of kilometers, floating in perfect formation, listening for ultra-long wavelength gravitational waves. Such missions, LISA, DESIGO, BBO, could reveal mergers of primordial black holes or vibrations from the universe's earliest transitions. And beyond all these devices lies the dream of a final frontier instrument, a detector placed near a supermassive black hole's event horizon, using gravitational lensing to amplify the faintest signals from the cosmic beginning. This instrument exists only in theory, but so did every tool humanity once placed in orbit. As the chapter approaches its emotional center, the camera reveals a quiet laboratory illuminated by dim blue light. Elderly instruments rest on shelves, early cosmic detectors, vacuum tubes, cryogenic amplifiers. These relics remind the viewer that the pursuit of origins is not merely technological. It is deeply human. Every telescope, every laser, every satellite is a testament to a species that refuses to accept the limits of perception. Each device embodies a fragile hope placed against the enormity of the cosmos. The narration softens, philosophical. The universe is vast beyond comprehension. Its forces indifferent, its beginning buried beneath epochs where time behaved wildly. Yet humans continue to build machines, delicate, fallible, transient, because something within consciousness cannot bear the silence. It must ask how everything began. It must search for echoes of the first moment. And in doing so, it becomes part of the universe attempting to understand itself. The camera rises from Earth into the star-woven darkness, revealing every observational tool, web, ground observatories, pulsar arrays, detectors, connected by thin threads of purpose. The chapter closes on a truth that lingers like a cosmic hum. Humanity may never fully witness the beginning of time. Yet with each machine, each measurement, each fragile leap into the unknown, it draws closer to hearing the universe's oldest whisper, the moment where existence first took shape, that in the dimmest hours of cosmic imagination, where language falters and mathematics strains against the edges of the unknowable, a final question lingers like a faint ember suspended over an infinite dark. What does it mean for something to begin? The universe, with all its blazing galaxies and quiet atomic arrangements, is a monument built upon an ancient paradox. Every star, every breath, every fleeting arrangement of matter owes its existence to an instant so compressed, so profoundly hidden, that even the laws designed to explain it dissolve under its intensity. Here, at the threshold between presence and absence, lies a mystery untouched by time. A mystery older than hydrogen, older than gravity, older than the first trembling shimmer of light. If the cosmos emerged from nothing, what is the architecture of nothingness? If the cosmos emerged from something, where did that something rest before time existed to cradle it? Scientists reach for equations that flicker like fragile lanterns in a windstorm. Philosophers reach for metaphors that crumble under their own weight. And humanity, tiny, ephemeral, earnest, looks upward into the night sky, searching for a story that explains why there is anything at all. As the camera drifts across interstellar voids, gliding past the faint afterglow of the first light, the question grows larger, quieter, more patient. It no longer demands an answer. Instead, it invites contemplation, a stillness where beginnings are not events, but reflections. A place where the universe, for a moment, seems to pause, as if remembering something it can never reveal. The camera enters a vast expanse where galaxies appear as scattered islands of fire adrift in an endless, ancient sea. Light glitters along the edges of spiraling arms, carrying the memory of billions of years. Yet beneath this luminous expanse lies the deeper silence the chapter seeks, not the silence between stars, but the silence before stars, before space, before time itself shaped the contours of existence. The universe observes no boundary except the ones humans create to understand it. But in seeking the moment of origin, even these boundaries begin to fracture. Concepts like cause, beginning, and time lose their familiar grounding. And so the exploration becomes philosophical, not because science fails, but because science reaches the horizon where thought itself begins to bend. In the depths beyond measurable time, the camera drifts into a serene, empty region where gravity offers no pull and radiation casts no glow. This is not the vacuum of modern physics, full of virtual particles and restless fluctuations. This is an imagined asymptotic edge, a symbolic threshold representing the purest form of before. Here, there is no motion, no direction, no unfolding, and yet, from this stillness, everything emerges. Scientists once spoke of nothingness as an absolute void. Now, even emptiness appears crowded with possibility. Quantum fields hum quietly beneath existence like a hidden choir. Fluctuations appear and vanish in the blink of a hypothetical moment. Symmetries break themselves like fragile ice fracturing under unseen pressure. And in these tremors of the smallest scales lies the first whisper of a universe capable of becoming. But the philosophical puzzle deepens. If quantum laws shape the birth of space-time, where did those laws originate? Were they born with the universe, rising simultaneously like structures crystallizing out of cooling vapor? Or do they sit beyond space-time, eternal and unreachable, forming a kind of mathematical scaffolding that reality momentarily drapes itself upon? Theories diverge, yet each points toward an unsettling truth. Beginnings do not behave like beginnings. They do not unfold like stories. There is no before, no empty corridor where events line up in sequence. In a universe where time is woven into space itself, the origin of one is the origin of both. Asking what happened before time becomes as paradoxical as asking what lies north of the North Pole. Still, humans continue to ask, not because the answer is near, but because the question shapes the meaning of existence. The camera glides toward a supermassive black hole, its gravitational horizon shimmering like a cosmic boundary between knowable and unknowable. Within this gravitational well, time stretches under immense curvature, slowing into near stillness. The viewer senses the symbolic parallel. The closer one approaches the frontier of cosmic birth, the more time itself unravels, slowing until past and future merge into a singular, unreadable moment. It is here that philosophical thought gains a new perspective. Many cosmologists propose that the Big Bang and a black hole share mathematical kinship, both residing where Einstein's equations lose clarity and quantum mechanics must intervene. Some speculate that universes bloom from black holes, their interiors expanding into new cosmic realms inaccessible from the parent universe. Others see these ideas not as literal descriptions but as metaphors pointing toward an unseen structural unity. The camera moves deeper, entering a region that visually echoes the quantum foam, roiling, unpredictable, filled with tiny fluctuations that twist and collapse too rapidly to form stable structures. The imagery becomes poetic rather than literal, representing the theorized landscape where space-time was not yet smooth but flickered in restless, primordial motion. From this turbulent backdrop emerges a quiet reflection. Perhaps the universe never began in a human sense. Perhaps it transitioned, transformed, or unfolded from a prior state that cannot be described with familiar concepts. Loop quantum cosmology envisions a contraction before expansion, a cosmic heartbeat where the universe rebounds instead of collapsing. Other frameworks suggest an eternal sea of quantum states where universes arise like ripples on a boundless ocean. And deeper still lies a stranger possibility. Perhaps the universe is self-contained, needing no external cause or prior condition. Hawking's no-boundary proposal imagines space-time curving smoothly back on itself in a finite but edgeless geometry. In such a cosmos, beginnings are illusions created by limited perspective, much like mistaking a horizon for an ending. Each concept, whether mathematical or metaphorical, carries emotional weight. The fragility of existence becomes apparent, not because life is rare, but because the laws that permit existence are themselves improbable, balanced on the knife edge of cosmic parameters. The loneliness of humanity becomes profound, not because the universe is empty, but because its origin lies beyond all narrative frameworks known to the human mind. And yet, the wonder is overwhelming, for despite this abyss of uncertainty, the universe continues to reveal its patterns, allowing humanity to glimpse fragments of a story too vast for comprehension. The camera rises from the quantum realm and returns to the interstellar medium, where clouds of hydrogen drift like translucent veils. Stars burn quietly in the distance, each a monument to the unknown forces that set reality into motion. A sense of cosmic patience permeates the scene. Nothing here is hurried. Nothing here seeks explanation. Existence simply unfolds, carrying within it the echo of origins too deep for human memory. Philosophers often ask whether laws create the universe or the universe creates its laws. Physics answers with equations, but the emotional truth runs deeper. Humanity seeks meaning not in the mechanics of creation, but in the fact that creation occurred at all. The camera drifts across the Milky Way's edge, showing billions of stars stitched into a luminous arc. With each passing moment, the viewer feels the boundary between science and wonder soften. The question of origin no longer demands resolution. It becomes a meditation, a quiet cathedral of thoughts suspended in the dark. What if the universe began from silence? From chaos? From a self-assembling mathematics so intricate it becomes indistinguishable from existence? What if the cosmos is eternal, cycling through phases of contraction and expansion, each new birth a transformation rather than a beginning? Or what if reality is a transient flower blooming briefly in an infinite quantum field, destined to fade into the same silence from which it rose? Each possibility is tender, profound, humbling. Each invites humanity not to solve the origin, but to sit with its unknowable depth. And so the chapter closes not with certainty, but with stillness. The camera rises beyond galaxies, beyond filaments, beyond the last wisps of cosmic radiation, until the universe appears as a faint glow suspended in darkness, a fragile lantern drifting through eternity. Nothing more can be said. Nothing more is required. For in contemplating the beginning, humanity discovers not a moment in time, but a mirror, reflecting its own longing to understand why existence chose to bloom at all. The universe remains silent. But in that silence lies a promise. That wonder itself is a kind of answer. And the story, like the cosmos, continues, softly, infinitely, beyond the horizon of knowing.